So last class, we started this proof, proving there's only 5 regular polyhedra, right? 3-dimensional regular, you could also say they're 3-dimensional regular polytopes. And the proof kind of uses a bunch of different things from previous sections that we've been talking about, right? So the first thing that we ended up using was Euler's formula. Okay, and then we multiplied this essentially by -4, and the reason we did that is because then you'll get a 4e here, which we can decompose into 2e plus 2e, and then we had from before we knew that that 2e is equal to these two sums here, right? So k times f sub k, and the sum over all k's. Same thing for k v sub k, and then we V is just the sum of the VKs and F is the sum of the FKs. So then we reorganize this to get this equation. And this is true for polytopes in general. So this would, well, technically convex polytopes, because that Euler's formula is only, this one is only true for convex polyhedra. Okay. If you wanted a non-convex polyhedra, it's more general. And if you wanted higher dimensional things, it's more general than that too. But for 3-dimensional convex polyhedra, that's fine. So up to here, we haven't used the regular condition, but once you suppose that it's regular, right, meaning all of the faces have to be congruent regular polygons, so 2-dimensional regular polygons of the same size, okay, and the vertices, every vertex meets the same number of faces, right? So it's a pretty strict restriction, but once you suppose this, then you're not going to have faces where the k's vary, right? There's just going to be one face type, right? Every face will be bounded by the same cycle size, and every vertex will meet the same number. It'll have the same degree, right? So what that means is this sum will actually only have 2 terms in it, right? Well, this sum will have 1 term in it. This sum will have 1 term in it. So up here, the right side has 2 terms, right? So there'll be some s where the number of faces is equal to the number of faces bounded by some s cycle, meaning that it's this polygon with s sides on it, and all the vertices will be vertices of degree t. Okay, so then we get this nice formula. We'll just call that star. Okay, so once you suppose that it's regular, this simplifies drastically. Okay, and from the previous lemma on this page over here, which we said that at least one face of every polyhedron is bounded by a k cycle for some k equals 3, 4, or 5. If it's regular, everything has to be the same face type. So what that means is that it severely limits what you can even have for a regular polyhedra, meaning you can either have equilateral triangles, squares, or pentagons, and they all have to be the same size, right? So that means S could be 3, 4, or 5. And then also, all polyhedra are planar. You can draw them in the plane. You know, I should give you a printout of this, actually. You can, let me show you what that looks like. I think I have, here. All of the, well, I'm kind of spoiling it by showing you the 5, but every polyhedra that's convex, you can draw in the plane, right? So the 5 that we'll get to, you can draw these in the plane, and so they're planar. And we had a theorem from before that says all planar graphs contain a vertex of degree 5 or less. So if you're talking about regular, where all the degrees have to be the same, then that means this t can only be 3, 4, or 5. Okay. So at the moment, you've narrowed down the number of possibilities from an infinite number to 9, right? 9 possibilities. So you could have s as 3, and then 3, 4, 5, and so on, right? But if you look at the possibility of both s and t being greater than or equal to 4, then you'll get in then star here, it's not possible, because this will be greater than or equal to 0, and this will be greater than or equal to 0, and then that would mean -8 is greater than or equal to 0. So what that means is one of these parameters has to be strictly less than 4, but the smallest that they could be is 3 here. So what that really means is one of those has to be 3. So what that means is you have 5 cases to consider. Okay. So let's write out all those cases. Okay. So case 1 let's see what happens when S and T are both 3 first. All right, well, I guess I'll just use this then. So case 1. Suppose S and T are both 3. Okay, now once you do this, you can now go up here and use this equation star and see what it'll tell you, right? Okay, actually, we don't even need to use star. We can actually just use, well, let's maybe just use star. Well, let's see what star says. Okay, so by star, what would this say? So plugging in S is 3 and T equals 3 into this equation, we have -8 equals 3 minus 4 F sub 3 plus 3 minus 4 V sub 3. So -8 is equal to negative F3 minus V3, right? In other words, 8 is equal to F3 plus V3. Okay, so this is one equation. And there's another thing that we know from before also. Let me just remind you that 2E will be the sum of what? 2E will be the sum of K V sub K and the sum of K F sub K, right? You guys remember this? So we can use these ones as well, right? So what would that tell us? So 2E is equal to, now if it's regular, these are only going to be one term, right? So you'll have 3 V sub K is equal to 3 F sub K, or F sub 3, sorry. These are 3 V sub 3 and 3 F sub 3. Okay. Again, this is because S and T are 3. Okay with that? And it's regular, so these are only going to have one term in them. Okay. So in other words, what does this tell you? V3 is equal to F sub 3. Okay. And now you have two equations and two unknowns, right? So you have this equation and you have this equation. So if you substitute that up here, so we have 8 is equal to V sub 3 plus V sub 3. So 8 is 2 V sub 3. So V sub 3 equals 4. And F sub 3 is equal to V sub 3. So F sub 3 is also equal to 4. Okay. And what does that tell us? Well, this is telling you about the geometry, right? So this is saying that, well, can you guys tell me what this Yeah, there's 4 vertices and they all have degree 3, and then there's 4 faces and they're bounded by 3 cycles of congruent polygons that are 3 cycles, which are triangles, right? Okay, so this is also going to be equal to V because it's regular, right? And this is equal to F since it's regular. Okay, since regular. Okay, so we have so what is this? So 4 vertices of degree 3. That's what that's kind of saying. And this is saying we have 4 faces that are equilateral triangles, right? Regular 3-gons, if you want to call them that. Just if you wanted to generalize this. Now, how many edges would you have? How do you figure that out? Now you just go back to Euler's formula, right? So by Euler, actually, you don't even need that. You could use this formula too. So you could use Euler or this formula, right? So 2E would be what? 3 times V sub 3, which is 3 times 4, which is 12. So that tells you that the number of edges is 6, right? Okay, 6 edges. And the only geometric figure that'll satisfy this is the tetrahedron. So right. So now you have to do this process pretty much 4 more times to get all the other ones. Okay. But the nice thing about this is notice as you're doing this, you're actually classifying not only just the number of vertices, edges, and faces, but you're also describing the degrees of the vertices and also what those bonding face types are. Okay, so it's a pretty strong description. Okay, so case 2, let's say that you're still using equilateral triangles, and now t is equal to 4. Right? Okay. So again, going back to our intuition, you guys kind of see what's going on here. You're just starting out with triangles. If I have one triangle, I'm not going to be able to build a 3-dimensional polyhedra with that, right? If you tried to like connect one edge to another edge, you would get this curved, like cone-like thing, right? And then if you go up to having 2 equilateral triangles that are meeting, and I start to fold it, if I try to fold this over to this, then it would just become a flat triangle, right? But so this is out and this is out. So the first instance where you have sort of 3 equilateral triangles meeting at a vertex here, and you start to fold it, so folding this edge over to this edge, then you'll actually start to build a 3-dimensional figure, right? And this is the one that'll give you the tetrahedron, right? Do you guys kind of see? You see the 3 faces? I don't know. At this vertex here would correspond to this vertex, right? Do you kind of see as I fold this over? And then now we're looking at this situation. Suppose I have 4 equilateral triangles meeting at a vertex. And now I'm going to fold this over, right? And do you know what that's going to give you? So if you had 4 equilateral triangles, it looks like it's going to make a pyramid, right? At least at this vertex up here. But this can't be the solution. Why not? Yeah, it's not regular because the base is a square, right? But you can keep using these, you can keep using triangles, and you'll actually end up with the octahedron. Okay, so it'll actually look like this in the end. So every vertex kind of has this sort of folded structure here. Okay, so this is this situation we're looking at now. So S is 3, right? Meaning there are regular 3-gons, and t equals 4 is telling you the degree is 4, right, for every vertex. So when I put these together, do you see that it's creating this 3-dimensional angle, right? That's kind of the intuition here. Okay, so let's see if that really does happen. Again, by star, I don't know if we want to actually solve all these. Maybe we'll skip some steps. Is that okay? Maybe I'll tell you what the 2 equations are, and then I'll just spoil the solution, okay, because you guys know how to do all this. Okay, so by star, you would get -8 is equal to -f3. And the reason for that is if you plug in t equals 4, that term is going to be 0, right? Because it was t minus 4. Okay, so, and the second equation from the 2e thing that you'll get is 3f3 is equal to 4v4. Okay, so now you have 2 equations, 2 unknowns. Well, actually, this one immediately tells you F3, right? It's 8. And then that'll immediately tell you this. So it is a 2 equation, 2 unknown system, but it's a pretty simple one. And V sub 4, just plugging in this and then divide over by 4 should be 6, right? 24 divided by 4 is 6. Yep. Okay, so what does that look like? So you have 8 faces, regular 3-gon, i.e. equilateral triangles, so 8 faces, and the degree is 4, right? So you have 6 vertices of degree 4, and then from this you can also figure out the number of edges again, right? And how many will that be? So 2e would be equal to what? So let's do, just making sure I'm plugging in the right thing. So the f here would be 3, right? So 3 3f sub 3, right? So there should be 12 edges. Okay. Does this look right to you guys? Okay, so again, V would be 6, E would be 12, and F is 8. But not only do we know this, we actually know what the structure of those things are, right? The degree and the face type. Okay, so we get an octahedron. So just be aware that that square is actually not a face; it's internal to the structure. Probably not amazingly drawn, but it's hard to draw them. Maybe it's better to draw the square first and then draw 2 vertices and then connect them. What do you guys think? It looks pretty much identical, but whatever. Octahedron. Of course, the reason that some of these are going to be difficult to draw is because you're trying to draw a 3-dimensional figure in 2 dimensions, so you're going to lose some sort of spatial data by doing that, right? You can think of this as like the shadow of the object. And if you look at their planar embeddings, they're going to be even more distorted. Actually, I have some pretty good pictures here. Okay, so looks like that. I mean, this picture is a little bit nicer because the distances are also drawn a little bit better. Okay. But if you want to draw it as a planar graph, right, this is going to be even more distorted because the actual polyhedron is supposed to have the distances are all the same. So when you draw the planar embedding, you kind of ignore distances, but you could just say that supposing these distances are all equal in the real geometric structure. Which, if you think of the shadow analogy, that's pretty good because you can't, depending on where that light source is, that can distort lengths, right? If it's close to sunset, you could be like 60 feet tall. Okay. Yeah, yeah.
So there's a lot of restrictions here, but is there any way to draw those like that don't give you the polyhedra? Like maybe it's not a planar graph. Well, I guess then other cases would be weird.
Draw them so they're not planar. Oh yeah, there are certain types of drawings of some of these figures that you don't care about crossings. You might care about some other parameter.
But is there a way to, like, given like these stipulations, to draw so it's not the octahedron?
Oh, I see what you're saying. Well, in this particular way that we've been setting up everything, because we've assumed that the thing is going to be regular and it's a polyhedra and it's convex and it's planar, all of that stuff together, like pretty much nails down this possibility. But if you were to solve a more general version where you do not have to follow, say, Euler's formula, you can have perhaps some non-convex polyhedra or something a little bit more general. Yeah. I don't know if that answers your question, but yeah. Well, there are things out there called the what are they called? I'm trying to remember. Archimedean solids and Jensen. There's another name. There's another family of polyhedra that have nice conditions, but they're not as strict as these regular conditions, right? So I think those types, you might be able to have more than one face type, for example. Maybe you could have equilateral triangles and squares or something like that. And then from those 2 types, what kind of structure could you build? So if you still impose the convex condition, you could still use Euler's formula, but then you might be able to build up some other interesting structures. Oh, one that's really interesting is if you don't suppose that you have regular n-gons. Let's say you have rhombuses. You can build structures from those things as well. Or when I showed you the, what was it? The geodesic domes and spheres, there you are still requiring all the faces to be the same and the same size, but they do not have to meet at the same number of degrees. So you relax the degree condition there. So yeah, there's other family types out there. It's just the regular is ridiculously strict because you're saying all the faces have to be the same and all the vertices, and they have to be the same size, and the vertices all have to have the same degree. So you could either relax the degree condition, or you could relax the face type condition and say, could you build it from, I don't know, pentagons and squares or something like that, and see what you could get. Yeah. Any other? Yeah, I think there's like 60 Archimedean solids. Yeah, so the classification gets a little bit more ridiculous when you try to generalize this.
Yeah.
That's just in 3 dimensions too.
Right.
Yeah. Yeah. Okay, and then the next type would be what? S is 3 and T is 5, right? So S is still 3, T is 5. So this one gave us the octahedron. Next type, you would have equilateral triangle and 5. And now notice I'm getting sort of to the extreme condition where if I have one vertex meeting 5 faces, I still have a gap, so I can potentially build something from this. And I'm not going to draw it for you, but we're going to get the icosahedron. Okay, because this angle is so wide, I don't know how to explain it. It's pretty close to flat in a sense. The flatter that internal angle is going to be, it's going to have to be larger in this. You're going to have more of them. It's going to become more spherical like, right? Which is exactly what happens with this icosahedron, right? Like a virus, right? Blessings. Okay. Let me just give you the parameters and the solution for that one. So case 3. So S is 3, T is 5. I'll kind of spoil this for you again. So plugging into the star, you get -8 equals negative F3 plus V5. And you'd, from the 2M, the double 2M equations, you get this. And you'll be able to get that there are 20 faces of these equilateral triangles, and there are 12 vertices of degree 5. Okay, and this will give you the icosahedron. And from this, you should be able to get the number of edges, which is 30, right? Right, 20 minus 30 plus 12 would be 2, right? Yeah, so 30. Or you could do the double E being this thing. The 2E. Okay. Is it okay if I don't attempt to draw the icosahedron? But I could show you it, right? It looks like this. When I took this class, my teacher made us memorize the planar embeddings of these things, which if you draw them like this, they're not terrible to memorize. Like this one is sort of the central component of it. And then you have these sort of 3 external vertices. But again, this one's even more distorted, right? These are all supposed to be the same lengths. Okay, a little better drawing it like that. Okay, case. Now, there's not going to be any more for S3, right? Now, we proved that, but is there some intuition there, right? So these are the 3 cases where S is 3. So what are the last cases to deal with? Case 4 would be S equals 4, T equals 3. And then, so remember, one of them has to be 3. So either S is 3 or T is 3. So then the other possibility, the last one, will be S is 5 and T is 3. Okay, because if S can't be 3, then T has to be 3. The other cases are impossible figures. You can't draw them. Okay, but I wanted to make sure there's some intuition behind this. Do you guys see why you can't, if you try to add in a sixth, equilateral triangle here, this is kind of what I was mentioning before. There's no gap now, right? There's no foldable, there's no space, and the edges of these triangles are already met. So this is not going to give you a three-dimensional figure. Instead, you would actually be planing, you would plane the, you could tile the plane with these equilateral triangles. So there's nothing to fold, right? In the sense of satisfying the regular condition, which means that all the vertices have to meet the same number of equilateral triangles. So you've exhausted all the possibilities for equilateral triangles in three-dimensional space while trying to satisfy the regular condition. You can, of course, have the base look like this and then build other polyhedra, but if you want all the vertices to meet the same number of faces, it's impossible to have any more than 5, right? So that's the intuition there. But we proved it. It's just nice to see there's some intuition. And then when you go to the next figure that you have, this is with triangles, then you try it with squares. Well, if I have one square, I'm not going to be able to build a regular polyhedra. Like if I start to glue the edges together, you're going to fold it. You'll make this sort of conical type thing. So it's not going to be classified as a convex polyhedra that's regular. And then if I have 2 of them, and if I try to bring them together, now you would just flat, it would be flat, right? If I try to meet this one to this one, it would either be flat or this non-polyhedral type figure, right? So this is out. So then you need at least 3, okay? And now there is a gap, and when I put these edges together, it will create, well, from that, you'll create a nice corner of a cube, right? Right? For example, at this vertex, you see that you have 3 faces meeting it, right? You have this top face, the back face, these 2 back faces that you can't see, right? So this should give us the cube, okay? But if I have 4, what's the problem here? Same thing, right? You can tile the plane now with squares. So this is out. In terms of building a regular polyhedra, because if I had to have every vertex be like this, then this vertex also has to meet 4 squares. You guys see that? So it would start to tile the plane. Does that make a little bit more sense now? What I was kind of talking about? Okay. So I'm not saying that you can't do that with polyhedra. It's just the regular condition is forcing it to have very few possibilities. So this one should be the cube. And it is. So I'll just spoil it for you and tell you what the numbers here are. So again, if you plug it into our star equation, well, if S is 4, the first part of that equation is 0. So you actually just get this, which will tell you immediately that number of vertices of degree 3 is 8, right? And the second equation from the 2e equals and the 2e equals will give you this, which will tell you that F4 is 6. So, right? So you have 8 vertices of degree 3, and you have 6 faces that are regular fourgons, otherwise known as squares. So this will give you the cube. How many edges will we have? I mean, you could just think of the cube and figure it's 12, right? Or you could use Euler's formula, right? V minus this plus this should be 2, right? And then last, you have another strange one, which is you've exhausted all the possibilities for squares by our intuitive drawing here, somewhat intuitive. So then the next figure is, okay, I've done triangles, squares, next would be pentagons, right? So then you can't just use one pentagon, same reasoning. You can't use just 2 pentagons, right? Your brain doesn't want, my brain always wants to draw hexagons when I'm drawing pentagons. So it's really messing with my brain here when I'm trying to draw this thing. But if you glue those together, they're going to end up flat on top, right? trying to keep the polyhedral structure. So you need at least 3 of them. Now, as soon as you draw 3 of them together, there is a small little gap there, right? And they can be folded together. So this edge will meet this edge. Now, just like the intuition I was saying before with this icosahedron, there is this small gap. But when you have a small gap like that, the 3-dimensional angle that you make is going to be it's close to flat, right? So what that means is this should be a spherical-like figure, probably going to have many faces, right? It actually doesn't have that many, but it still is, it's sort of one of these more spherical ones, right? In the sense, do you guys see that as that angle gets larger, you're going to have more faces and more spherical like, so that you're going to get this dodecahedron. And this is the only one that you can build with pentagons, because I can't cram another pentagon in that little gap right there, right? So anything larger than this, you're not going to be able to do, but this will give you the dodecahedron. And then the next figure you go to is hexagon. But the problem with hexagons is as soon as I put 3 of them together, you're going to tile the plane, right? As B's figured out, right? So if I have that vertex has to meet 3, then this vertex has to meet 3. And then that vertex has to meet 3, and so on, right? So maybe B's were trying to build a regular, 6-gon faced polyhedral thing, and then they ended up making nice hives instead. Right. So you're not going to be able to get anything from 6 or higher. I just thought this was kind of nice because there's some intuition behind why there shouldn't be more out there. Maybe it's believable. Okay. Okay. The equations for this one, you have, so plugging in S is 5 and T is 3 into the star equation, you'll have this. And then the other double equation, the 2E equation, will give you this, which tells you the number of faces that are these regular pentagons is 12. So I have to have 12 faces. Number of vertices that are degree 3, there's going to be 20 of those. And the number of edges is what? Yeah, it's 30. There actually is a thing called a dual, which maybe I'll talk about in a little bit. But this will give you the dodecahedron. Okay. Which again is this one. So do you guys see that every vertex has degree 3? Right? Every face is a regular pentagon, and there's 30 edges in that one. Okay, so you've classified all of them. If you try to go up a dimension and do kind of the same thing, where now you would want, you still want all those same conditions on the 3 dimensions, but now you want every vertex to meet a 3-dimensional chamber, meaning you would be building them from structures like this. You can continue the process. And I showed you the 4-dimensional one, right? The 4-dimensional one, you actually have a few more, but then I think once you get to 5, I think it's 5 actually. Once you get to 5, you actually only have 3 family types, which will be generalizations of the tetrahedron, the cube, and the octahedron. So these ones are sort of like exceptional families that only exist at low dimensions. And then there are high dimensional analogs of these guys in general. Like this one right here is actually the KN family, the simplex family. There's hypercubes in higher dimensions. And then this is called the orthotope or a cross polytope. Yeah. There's a nice geometric way to describe the vertices of this thing, which comes up in other areas. But, oh yeah. Well, the person that classified all these things in the higher dimensions, yeah, it's all geometry.
In the higher dimensions,
yeah.
is there like another like if you were to go up a dimension, would there be another?
Another parameter, yeah, it would be like the number of it should be like the number of chambers, which would be like the 3-dimensional figures that they all meet.
But you'd still have like the number of faces and the number of.
Yes, you'd still have that. So, so I'll show you the 4-dimensional thing in just a second. But one thing I wanted to do to see, well, first of all, we're done, right? We actually finally proved that there's only 5 platonic solids. Okay, so that's interesting. One thing that is also interesting is each of these shapes has what's called a dual. I might show you this later on, but like the dual is take your figure, and then now what you're going to do is, you know how with the line graph, what we said was the edges become vertices, and then you connect them. With a dual, what you do is the faces become vertices. Okay, so I'll have 4 vertices, right? Each of these faces on the tetrahedron. And then what you're going to do is you're going to connect them. I don't know if you can see that. It's hard for your brain to like think about this, but this is flat on the top, right? And then these go down. So do you see this is the dual of the tetrahedron is a tetrahedron. Okay, now let's try the other ones. I'm just showing you this. You're not going to have to remember this. All right. There's just some other avenues that you can go with some of this stuff, and you can generalize it to graphs too. You can have the dual of a graph, because a planar, as long as it's planar, you know how to draw the dual if you have regions, right? Okay, using kind of the same idea. So now draw a vertex for each face. How many faces are there? There's 6, right? So you see the dual of a cube is an octahedron. And I'm not going to draw these ones, but if you stare at it for a little while, okay, you can take this dodecahedron and think of it as inside of this. And if I can kind of give you a little intuition there, like let's look at the icosahedron and just pay attention to these 5 faces that are closest to you. Okay, you're gonna connect the corresponding vertices if they share an edge. Okay, so the edges connecting them will cross over the edges connecting here. Okay, and then these vertices are the things that actually become the faces in the dual. So you see what you end up with is a pentagon. You see that? Okay, so faces become vertices, vertices become faces, and edges become edges, and they're going to cross over each other. Right? So you'll end up with a figure, and this dualization process, if you again look at this here, look at this. So tetrahedron, if faces are supposed to become vertices and edges become edges, then those parameters should stay the same. So you see it should be 4, 6, and 4. But look at this. If a cube's dual is an octahedron, then faces should become vertices, vertices should become faces, and edges should become edges. So you see that? And then down here, in the dodecahedron, the dual, the vertices should become faces, faces should become vertices, and edges become edges. So there is sort of a dual for each of these. I don't know if that's interesting to you, but there's another reason that all these kind of match up in this sort of nice, perfect way, right? Maybe now I can show you regular for polytopes again. Hang on, let me share the screen real quick. Okay, so if you increase this requirement that, let's look at the 5 cell. Okay, so this would be, if you go up one more dimension, okay, if you go up to 4 dimensions now, and you want vertices to meet the same number of chambers now, so 1 dimension lower than, if you're in 4 dimensions, the vertices are 0-dimensional, but the chambers will be 3-dimensional, okay? So do you see that each vertex, it's kind of hard to see this, each vertex is meeting a tetrahedron. You see that? So there's this one tetrahedron that's closest to you in the foreground. There's a tetrahedron that's over here on the left, and a tetrahedron that's, I don't know, depending on where you're standing. I guess this is on the right side, right? And then there's another one in the back side here, sort of. There's also, like, you can think of having an outer tetrahedron, and because you see each face, there's 4 faces there. So there's like an outer tetrahedron. Like, for example, the one in the center, how many tetrahedron is it meeting? That one's probably the easiest one to look at, because you see that there's a little pyramid on the bottom, right? Little tetrahedron, okay? You have a tetrahedron over here. You have a tetrahedron over here, and you have a tetrahedron towards you. So there's 4, right? So every vertex is meeting 4 tetrahedron if you include the outer tetrahedron that you can't really see. It's similar to how you had this outer face, okay? But the reason for that is because you're trying to visualize this 4-dimensional thing, which you can't visualize. So you have to project it down to 3-dimensional space where all these edges are supposed to be the same length too. Now, if you project it all the way down to 2-dimensional space, you'll get a nice graph, which is actually just K5. Okay. But you lose a lot of information by doing that, right? You don't see the 3-dimensional chain, you don't see the tetrahedron that are in here, right? You can kind of think about how they're in there, right? Because they're K4s, right? The tetrahedron. But this family, you can actually keep building the same thing in higher and higher dimensional space and have those more general requirements. The 16 cell, this thing, I could try to show you the picture of this. This one, each chamber inside of this one is an octahedron. So you can see one of these octahedron here, maybe. Wait a sec. Actually, the way that they drew it, it's really hard to see that. Actually, I think the 24 cell is the octahedral type. Hang on a sec. Okay, that's horrible.
Yeah.
Yeah.
The
yeah, actually, let's look at the 120 cell. This one's interesting. So the 120 cell is the 4-dimensional analog of the dodecahedron. So do you see that you can kind of see how there are these dodecahedral chambers inside of the thing? Maybe in the very center, you can kind of see the dodecahedron. The chambers that are closer to you, you can kind of see they're dodecahedral, right? But yeah, it's called a 120 cell because there's 120 of these dodecahedron. Those are the cells. You're building up a cellular structure from these dodecahedral things. And it's still trying to satisfy all those regular conditions. So what's weird is when you go up 1 dimension, you actually end up with more of these sort of analogs of the Platonic solids, right? But I think as soon as you go up 1 more dimension, dimension 5 and above, and you try the same thing, you end up with only 3 family types. You only end up with the simplex, this cross polytope, the orthoplex, and the hypercube. That one's not terrible to look at. Like this one, do you see that each chamber is a cube? You got this chamber in the center, you have a chamber towards you, and so on. And each vertex is meeting a certain number of cubes. Okay. I don't know. If you wanted to see that, I thought maybe it could be interesting, but yeah, you can try to, this is another avenue for trying to generalizing what we're talking about here. And of course, you can also look at the median solid. I don't remember how to spell that. Yeah, so see, these Archimedean solids, you do not require the faces to be all the same. So this one's built with this one has hexagons and triangles. This one has squares and triangles. I don't know what just happened with the projecting, but somehow searching that made it purple. Yeah, I think so there's quite a few. I think the 60 that I was talking about, there's another family as well that's similar.
I have another weird question.
Yeah.
So we can draw planar graphs of these regular polyhedra in 2 dimensions. They define like, it wouldn't like be planar graphs, but like a 3-dimensional planar graph. like, can you draw like a 4-dimensional graph?
Yeah.
Dimensions?
Yeah, so the analog and higher dimensions would be like, you don't want these cells to overcross each other. And in
Yeah.
topology, there's stuff where you would consider these things like certain types of simplexes and things like that. It's kind of related to some other things that you can do in graph theory called, well, we'll probably talk about them, hypergraphs as well. Yeah, once you go up to 3 dimensions though, any graph can be embedded in 3-dimensional space because you have now enough dimension for the lines, right? As soon as you go 2 dimensions higher than your highest dimensional structure, then there's enough room for the thing to kind of like move through. But if you had to build something in 4-dimensional space and the chambers were 3-dimensional, now there's a possibility that they're going to cross over each other and stuff like this. So yeah, it's pretty complicated in general. Yeah. Oh, this is a truncated icosahedron, which is the soccer ball or football, whatever you want to call it, depending on what country here wants to name the thing. But do you guys see how you would actually get this? Is you can actually take, it's called truncated icosahedron because you can take these, you can take like slices off of, let's go back to, stop sharing this. If you go back to the icosahedron, instead of building the dual, if you actually make slices off of these vertices, okay, you would build a bunch of these pentagons, but if you slice them so that they're not right next to each other, then there would actually be a gap, and that gap is where you'd also get those hexagons, right? So you'd have pentagons, and you'd also have hexagons. So just truncated as if you just sliced off part of these vertices. So you'd get pentagons for each of those, but then there's still some gaps. When you look at the dual, there's not going to be any gaps because they have to be actually immediately connected. It's as if you almost sliced it and they're right next to each other, right? Okay. So there's a lot of other avenues to generalize a lot of this stuff, actually. Okay. But yeah, I think that's good enough for now. So next Friday is the exam, right? So I think Wednesday we can do a review, and then Monday we'll just start some new stuff, okay? But it won't be on the exam, right? And whatever I gave you to practice, I gave you a homework that was due, and there's a couple other practice questions, just a couple other, they're homework looking type things, but they're just more practice questions. Did anyone have a homework question? If not, you guys can have a good weekend, but if anyone did have a homework question, just let me know. All right?
It's not really to do with the homework, but I was doing the homework and I thought of something.
Mhm.
Is there a way to color a graph so that you can find like a tree, like a spanning tree of it?
Color the graph so you can
I
find
mean, you
the
can
thing.
obviously color the graph so that you have a spanning tree, but like just maybe with restrictions, I don't know. It's just something I was thinking about. So that like one, maybe like if you alternate colors every time, like if you have 3 colors, red, green, blue, and you alternate every color, then
Mhm.
it's a spanning tree or something like that.
How would you extract the spanning tree?
I don't know.
Yeah, we'd have to think about that a little bit. Like when we're going to talk about coloring soon, but the idea is kind of, think of it as, you can just think of them as numbers.
Yeah.
And let's just say, we'll say that the coloring is proper as long as adjacent vertices are colored differently, right? Or just or labeled differently in some way. So you could use numbers as well. Now for
Not from something like that.
yeah, like for example, if I look at, it might be a little difficult to use proper coloring to get it, because for example, if I looked at K5, now I have to actually use different colors for every single vertex, right? Because everything is adjacent. But this thing has a lot of spanning trees. So just knowing the coloring alone, like one spanning tree, like the tree is actually only going to need 2 colors, I think, in general. Because every spanning tree is bipartite. There's no odd cycles. And a bipartite graphs are easy to color because they'll satisfy that condition, because I could just color one with one color and the other one with another color,
Right.
right? Now there may be an algorithm in there somewhere that you're doing something to brute force find these spanning trees, but maybe you're not doing something with proper colorings. Maybe you were thinking of something else.
Yeah, maybe just like if there's like a certain restriction on coloring the graph a certain way.
There are brute force ways of finding the spanning trees where you just like start at a vertex and you're trying to go through the tree and you're trying to make sure that you visit every vertex, but also get a tree. So if you meet a previous vertex, you clearly make a cycle.
Yeah.
So you're not going to go down that avenue. So you would just continue walking,
Right.
and you would actually make sort of a depth tree, right? You'd start at some vertex. You'd start out by visiting one of its. So like, let's say that you had this graph. And you started here. You would start by looking at its neighbors. And then you would try to keep doing this process. Like, can I go to one neighbor and look at all of its neighbors and so on? So you kind of have this slow brute force algorithm. Yeah.
Yeah.
I don't know. I think there's a name for that.